So we're going to talk about exponential quantum advantage in a parallel universe, and this is joint work with Joe Carolan and Mahati Vempati, who are also students at University of Maryland. Also, I'm having a slight cold, so if I cough or sneeze in between the talk, I apologize. Yeah, it's so this is my first talk on this topic on this project. So it is totally possible that there are many things to improve, and I'd appreciate any helpful feedback. So maybe let's get started. So this is so let's parse the topic a little bit. So we all know and love exponential quantum advantage, but people might be a little bit like not too sure what does it mean to have a parallel universe. So this is a result in query complexity, and in particular parallel query complexity. So I will start by describing what does it mean. Oops. So I'll just briefly recall what query complexity is. So we are given a function and we want to compute it, and we are given the input as a black box, so we can make queries to the input. And so a classical query would look like the figure on the left, where I give you an input bit and you're going to give me the corresponding. Where I give you an input index and you're gonna give me the corresponding input bit. And a quantum query would just be doing this in a reversible manner, and you can also do this in superposition. And so we have a few models which are deterministic, randomized, and quantum query complexities. And so they have like they use certain in its definition it uses certain properties, and so for deterministic and randomized, the oracle we can use is classical. For deterministic, we have to answer with probability 1. For randomized, we have some leeway, and for quantum also we have some leeway. And for deterministic, since it's deterministic, it doesn't use random bits. So the point is that it's more fair to compare randomized and quantum, even though randomized is stronger. And so it's easy to see that quantum is always less than randomized, which is always less than deterministic. What if we are allowed to make queries in parallel in each step? So what if we can make p queries to our oracle at each step? So a classical p query would just be if I just give you p indices and you just give me the p input bit, the corresponding p input bits. A quantum query would also be pretty similar, that you do this in a reversible manner. So you're gonna give me a state with p indices and p output registers, and I just compute this. I just compute the input bits in the output register. So, and again, we have similar models, deterministic, quantum, and randomized. I'm not gonna go through this in detail, but the only thing that changes is the oracle. We are now allowed to make p-parallel queries. And so it's also easy to see that this relationship. And also one parallel query is a regular sequential query complexity. And also what could show some trivial bounds on the p-parallel query complexity. So one can simulate a p-parallel query. One can simulate a sequential query using a p-parallel query, because you could just ignore the p-1, the rest of the p-1 parallelism that you have. And one could also simulate a p-parallel q query algorithm by just making p times q queries in a sequence. So you have some non-adaptivity you can just choose to ignore. So we have these trivial bounds on p-parallel query complexities. I would also like to describe some Boolean complexity measures, which will not be super relevant, but it will help you give some context. This definition is not a complexity measure. So a function is a Boolean function is total when the domain includes all the inputs and it's partial otherwise. We also have a notion of certificate complexity, which is intuitively the minimum number of bits required to certify a worst case input. And we also have a notion of block sensitivity, which is the maximum number, which point input is the maximum number of disjoint sensitive blocks that you can have. Yes.
Sorry, just very clear. With certify, we mean we get like fx.
For certify, I just give you a subset of the indices, and if you just query that subset, then the function is guaranteed to have a certain value. So it can't change. So it only depends on that certificate. So for instance, for the OR function, I could just give you a bit that is 1. And then like whatever the rest of the bits are, the function is going to be 1.
Okay, yes, I see. Yes.
And so we also have a notion of block sensitivity, which is like the minimum, which for an input is the maximum number of disjoint sensitive blocks that you can have, and then you maximize over all inputs. So a disjoint sensitive block is basically so a sensitive block is basically a subset of inputs, which if you flip the value of the function. So that's why it's sensitive.
And when you say block sensitivity, like what does the block mean? Sensitive, I see. Like if I
so a block just means a subset of inputs, and then you want to choose disjoint subsets.
okay.
Yeah. If you don't like these measures, don't worry about it. It's probably not going to be very relevant. So what is known about the relationship between the query complexities for total functions? And we know that the deterministic query complexity can be at most the 4th power of the quantum query complexity for total functions. So they are polynomially related. And we also know that like this is somewhat tight, and for randomized we have a function that achieves the 3rd power. So we don't know what's between 3 or 4. And so the question that arises is that if we are able to make queries in parallel, does these relationship hold? Or and so before we talk about this question, I would like to first give you some examples of what is known about some functions, about the parallel query complexities of some functions. So for the OR function, which is our favorite one, we know that the quantum query complexity is just the square root of the classical parallel query complexity. And also for symmetric functions, we have a tight relationship. We know the tight bounds. I'm not going to describe it in detail. It's just an example. For element distinctness, we also know that the parallel query complexity is again the quantum parallel query complexity is similar to deterministic parallel query complexity as Q is to D. We get like power of 2/3, and this could be generalized to the problem of K-sum. And so here the thing that I want you to notice is that the quantum query complexity is just like a polynomial of the deterministic query complexity. So these are like pretty natural functions, and the question is that again, is this true in general for all total Boolean functions? So this question was actually studied by Stacy Ronald and Patrick Magniez, and they conjectured that for all total functions, these measures are polynomially related, and they also showed this conjecture for all total functions and for parallelism small enough. So if the parallelism is polynomially smaller than the block sensitivity, then you cannot have exponential separations. And the question arises that what happens when the parallelism becomes larger. So, any questions?
Polynomial, it's always in P, right? I mean, you say asymptotic notation, it's the parameter that you're taking. Asymptotic notation is P.
Oh yeah. So P is the amount of parallelism you're allowed.
If you really allow a lot of parallelism, like P equals N, then of course the parallel complexity is always 1, and it wouldn't unbound gaps.
But the classical would also be 1.
Oh,
There would be.
So it sort of goes, goes up and then has to come back down, I guess. Like,
It would never go up, right? Because if you allow more parallelism, then you can do more.
no, I mean a sort of a relative gap. So if I look at the ratio between the two.
I think the relative gap would also,
Oh,
at least for the examples that we have seen.
Yeah. But I assume you're going to say something dramatic now.
Well, not too soon.
For the record, I don't remember ever saying that.
Okay. So maybe we should talk about how to falsify this conjecture. So, what?
Okay, sorry, I just parsed that. Never mind, go for it.
So first we will describe the cheat sheet framework, which was used to achieve a super quadratic gap between quantum and randomized query complexities, which I've also stated earlier. So the cheat sheet function framework is used to make a partial function total. So how does it work? So we are given a total Boolean function. We're given a partial Boolean function, and we are also given an integer c. And what we will have is c instances of that function, and then we also have access to some extra inputs, which we'll call cheat sheets, and those will be indexed by your c bits. So you have 2 to the c cheat sheets, and the function is 1 if and only if the following conditions are satisfied. So firstly, the c inputs that I gave you, it should be in the domain of the partial function. And second condition is that once you evaluate those c functions, you get a bit string of size c, and then you go to the cheat sheet and you look at the corresponding cheat sheet that is indexed by the c outputs, and then that cheat sheet should certify 2 things. Firstly, the condition 1, that your inputs are in the domain, and secondly, that you're looking at the right cheat sheet, that the L sub i's are actually equal to. So it's kind of complicated in the sense that it's a little bit self defined, but the cheat sheet contents needs to certify 2 things. Firstly, your input is in the domain, and secondly, the index of the cheat sheet that you're looking at is the right one. So since your input is in the domain, you can evaluate functions. You can evaluate f on those inputs. And then when you evaluate those inputs, so the cheat sheet contents should somehow certify that when you evaluate those inputs, you will get those c bits.
This FCS function is total, right? Like that's.
Yeah.
It's a total function.
Yeah, thanks.
Little and smaller domain, right?
Huh?
You kind of shrink the domain by throwing away everything that you don't want. Like you kind of make a smart mapping.
Yeah, you're somehow asking your function to also verify, to also like kind of give you a proof that you are in the domain.
But it's actually a bigger domain. like
Yes.
the bigger domain, but then you make part of the function's job to check that the function only accepts if certain checks are passed, which are related to the promise on the original.
Function is total, but it will be zero on almost all. Okay. Is L also part of the input, or is the input just x1 up to xc?
Input is just x1 to xc. You also know the c.
Yeah, okay, get it.
No, sorry, the input, if I read it correctly, the input is not just x1 up to xc, but also 2 to the c cheat sheets.
Yes, so
And
you
how
get,
long is every cheat sheet? How many bits?
the c will take to be like around log n, like some constant factor, like for instance, 10 log n, that was chosen in the paper that described it. And then you have like polynomially many cheat sheets.
But how long is one cheat sheet?
Oh, well, it depends on the function that how many bits do you need to certify. So it would still be, it should be polynomial for the functions that we will consider. But it like this framework is kind of general.
But according to this definition, a cheat sheet is C bits, right?
You have 2 to the C cheat sheets. So I'm not right now describing the size of each cheat sheet. You have access to 2 to the C cheat sheets, but each cheat sheet should be long enough so that it could certify that the input is in the domain and it is the right cheat sheet to look at.
Okay. Why does it get multiple inputs? Why would it just
Because if you have one input, then it's easy to, then you don't need to compute f. You can just go to the cheat sheet. You can just directly go to the cheat sheet because you have query access to the cheat sheet as well. So you want C to be large enough, but not too large, because otherwise the input size would be drastic. Because we have 2 to the C cheat sheets. So you want C to be like log n.
Right, okay, but my cheat sheet kind of returns me if it's a valid input.
What?
And like if an xi is a valid input, this is in my cheat sheet, right?
Oh.
Yeah, yeah. The cheat sheet should be able to give you enough information to certify.
Or if it doesn't, then you reject.
Yeah. Yeah. Yeah, I'm just talking about the case where f is equal to.
So what does certify mean here? Is it you certify that it's in the domain, but you give, does it mean you check a certificate? Is there like another function which checks if it's in the domain?
So one certificate would be just to give you the whole input. And then since you know this function f, you also know its domain. And then you can easily check. But sometimes you can do better depending on how many bits you need to certify the function.
Or it could be some substrate.
So like the indicator function of the domain is also something you can have like a certificate for example. You could certify that it's in the domain faster. Anyway, never mind. You can just check it's in the domain in some way.
Yeah, you can just like give me the whole input. Like you can just copy the whole input and that would be a certificate. But you probably don't want to do that. So, yeah, and we also know that when C is large enough, having access to this cheat sheet is not helpful for any reasonable model of computation. So this is a useful fact that will come in handy. And now we want to define a canonical definition of a cheat sheet. So I'm just copying the cheat sheet framework here. And in the canonical cheat sheet, what you just do is you take f to be a composition of a function g, which would be some function which would achieve exponential quantum advantage. For instance, k-fold correlation. You can think it just needs to have quantum query complexity small and randomized query complexity large for our purposes. And you also take c to be something like 10 log n, right? Large enough, but still log n.
G can be a partial function unit.
I
Yes,
guess that's the key issue.
yes.
Yeah.
Yeah, that's, yeah,
You're smuggling in the partial function.
yeah. So. Oh, yeah. So any questions about this?
Still a little bit confused about the cheat sheets, but we'll figure it out.
I'm also confused.
Yeah. There's a lot of moving parts. But that's fine. Keep going.
So I guess now we should describe a quantum parallel algorithm. So first, I should say that even this canonical cheat sheet function achieves an exponential quantum parallel advantage. But it has its own, I mean, it's quite interesting, but it has, okay, I'll describe that later. So I'm just copying all of the stuff here, that we chose, the function to be, the canonical cheat sheet function to be the composition of G with and/or. And we also, and we chose and/or, or it was chosen in the paper which tried to separate Q and R, superquadratically. They chose it because the certificate complexity of and/or is n for and on n bits and or on n bits. So it's easier to certify. And so now we're ready to describe a. So
And or is that you take or of a string and then what exactly?
yeah, yes. So you get n square bits and you just divide it into n blocks.
Okay.
And then you take or of each of them, and then you get like n outputs, and then you take an end of.
So you have n squared to one
Yes,
function.
yes. And it's useful because its certificate complexity is square root of the size of the input.
Yeah.
So this is just a function with good certificate complexity.
Right. Mm,
Do you need anything else of it, or just that it has good certificate complexity?
I think that's how it says.
Yeah, okay, so you can pick anything here that has like sufficiently small within certificate complexity.
Right. We will do that later.
Okay. Very good.
Just for clarification, in the FCCS, then
Yeah.
you don't take n squared, but you take like n to the third. So you like, you don't, like G doesn't take one bit, right? It takes n bits.
Yeah.
So you have like many
Yeah.
of these triangles.
Yeah, so the input size of FCCS is n to the cube, and then you also have cheat sheets.
Mm.
So
Yeah,
it could be even larger. It
Yeah,
could be
yeah.
like n to the 10, n to the 15, whatever. How long your cheat sheets are, depending on what C is. So if you take C to be 10 log n, you have n to the 10 cheat sheets. And then the size of each cheat sheet would also be n square or n cube, depending on what function you use. So it's still polynomial. That's the point. And so let me now describe the quantum algorithm, which is kind of not too hard to follow. With n square non-adaptive queries, we can evaluate an input to G. Because that would be just meaning evaluating and or on n square bits. And we could just like query the whole.
Yeah, evaluating G or evaluating one of the input bits of G?
Evaluating one of the input bits of G.
Because the input to G itself is huge.
Yes, input to G is like n square bits.
Well, no, the input to G is some unspecified number of bits at this point, right? The input to FCCS is huge.
Oh, so all the inputs of G and then or are n bits.
Yeah, but G itself is a function on the number of input bits that you haven't specified. You told us what letter is
Oh.
for the number of input bits of G.
Oh, I'm sorry, I just took it as n. Oh, it's n. Whenever I don't specify it.
Okay, so FCCS has n cubed input bits, is that right?
Yes.
Yeah, yeah.
And so if you
And,
Yes,
And then a cheat sheeted version of FCCS has even more.
yes. Yeah, but still, it's still some polynomial as long as C is logarithmic. So we can do that, we agree. And now we want to compute. Yeah, so we want to compute G on one of the inputs. Since the quantum query complexity of G is K, we can compute G using K n square parallel queries. Because we can evaluate each input using n square with classical non-adaptive queries. And we just like compose it with a, yes.
I'm very confused now. Does the term input to G mean different things in point one and point two?
The bit.
Yeah,
that goes into G.
Yeah, in step one, you're talking about one input bit. In step two, you're talking
yes,
about.
computing G, computing G on an input.
So you're really talking about computing the output of G.
Yes, yes.
Ah,
Yeah,
okay.
I'm sorry,
Yeah, output of G can be computed using K parallel
yeah,
queries,
I
yes.
should have, yeah, sorry about that.
So do you do, is it or and G, or do you do G first? Sorry, I'm just very confused for a second.
Yeah, you do, and or first.
Yeah, okay, good. That's the normal way, yes.
Yeah. Yeah, okay.
But then it's output of F, right?
Huh?
Yeah, number two should say an output of G.
Actually, an output
Yeah,
of FCCS.
FCCS.
Right, yeah.
Yeah, it's,
Yeah,
yeah,
yeah, FCCS.
well, actually, that's also a typo, it's supposed to be F only, because FCCS is like the function F with access to G.
Oh, okay. Okay,
So,
okay. Yeah, so this is F, and then later
Yeah,
you can compute the output of F using K n squared parallel queries.
Right.
That's a statement that makes sense to me. Okay, I'm good. I'm happy. Yeah, okay.
I already apologize to you for it. This is my first time I'm talking about this project, so size up.
Sorry, I get very confused because an output of F, like usually when I have a query, I just put in like some index and then I get like one bit back, right? So is F not the function that I'm querying? So if I want an output of F, I just put in like a bit string and I get like, I query FCCS or whatever, and I get one bit back, namely if this one or is this zero. But that costs me one query, right? If I want to calculate one output bit of F.
So the input bit of, so the input size of F is n cubed.
Yeah, I understand.
Like F is this G composed with N
Yeah,
equals
yeah,
or, so you have to actually do work to get a bit.
It has some query complexity.
F is not the oracle. F is
Oh,
the input,
okay.
you have an oracle for those input bits.
Yeah, you don't have oracle for F, you only have access to each bit separately, so you have n cube bits. So, it, like the trivial upper bound is n cube.
I think we're calling inputs X here.
Yeah, no, I got confused about what my F is the property.
Work really well if it has a try.
Yeah.
There's a lot of moving parts.
Yeah. Yeah.
Okay, good.
You sometimes have tildes over the theta and sometimes not. Are there hidden log factors here?
Yeah, and so in order to compute L, we need to evaluate this function F on C, on C many instances, and C I chose to be log n. So then you can do this all in parallel because those instances are independent. So you can compute all of them in parallel. So you just have to pay a log factor in the number of in P and not in the number of queries.
How many bits is L again?
So L should be C bits. What is L again? So L was an index to a cheat sheet. So L is the answer you get from evaluating C instances of F. And so we now know L, so we can just go to the L cheat sheet and since the certificate complexity of n or is small, I could certify that an input of size n cube is in the domain of f using only n square bits. Because I could just certify each input to f using only n bits.
Yeah.
So then with at most n square bits, I could just certify. So we can choose the size of the cheat sheet to be n square, and that's fine. And since the size of,
So the C little n, should that be C capital N? Or is there just little n difference?
any little n right now should be a typo. Where is it?
Is there a little n?
Very last line, yeah, so C n, C little n.
Oh, CN, yeah, there should be a big N.
Oh, yeah, it's a capital N. Yeah, I use little n first, but then I later realized that I might need to use little n for something else. And change every little n to a capital N except for this one.
Hopefully.
Hopefully.
Okay, good.
So now we know the size of the cheat sheet is only n squared. So we can just like non-adaptively query with just n squared parallelism in only one query. Right? And that's what we're gonna do. So now we know the contents of the cheat sheet, and we also have evaluated f's.
So you've used K plus 1, correct?
Yes.
Yeah.
And now I only need one more query to verify conditions 1 and 2. Since again the certificate complexity is a small of n or is small, I could just look. I know all the contents of the cheat sheet, of the relevant cheat sheet, and I could use that to certify each input to G. And they're not too many. They're like n many, but I could do all of those in parallel. So I still need one more query. I might have some log factors in the parallelism, but that's okay. And so overall, we have a k plus 2 query quantum algorithm for computing this function. And here FCCS is not a typo, because we computed the cheat sheet version in k plus 2 queries.
Yeah, and the total input size was n cubed. That's sort of the relevant scale.
The total input size of each f was n cubed.
Yeah.
And then the cheat sheets could be larger.
Yeah, okay.
Right? And many of you might have already noticed.
Did it be K plus 3?
Oh, why?
I don't know, because I see 3 times, I think.
Oh,
One
we pay k to compute the f's, and then we go to the cheat sheet, we query the contents of the cheat sheet with one query, and then we come back and then verify with just one query.
Yeah,
So I might have,
just from counting the number of things where you say I query something, it's K plus 2. Two.
Yeah.
So 5 and 6 have 1, and then 3 has K.
K plus 3.
why?
Because 2
Oh, there's one all the way up top.
Mm.
Yeah, there's one evaluated input to G using one
Oh,
parallel
oh,
query.
wait, yeah, like number 3 is using number 2. So,
Yeah, explanation, it's not. two
Oh,
separate
oh,
queries.
okay.
It's not.
yeah, it's more of a presentation issue.
Yeah, okay. In any case, this is going to be a constant. It doesn't matter.
Yeah. So most of you, like many of you would have already noticed what's happening. So we have a quantum algorithm that needs k queries for some p, which is like n squared, around n squared. And we know that the randomized query complexity is n cubed. It's not n cubed, it's like, it goes to n cubed when k is large. And so therefore, now we use the trivial bound on the RP parallel using a lower bound for R to just remove a factor of n squared from this expression. And we get that the randomized query complexity has to be at least some polynomial, which we could increase as k. Oh, Yeah, M is the domain of the cheat sheet function.
Yeah, so some large polynomial.
Yeah, so some large polynomial. Right, right. So it,
Of the polynomial.
yeah, so the separation we get like from this is like 1 versus n to the 1/24. Because M is huge.
Oh, yeah, like,
So
yeah.
separation is not, like, we don't worry about that for now. But then this is, okay, another thing I wanna have then. Battery is running low.
Oh, boy.
Your battery or?
Yeah. Should I bring a charger quickly or?
Does this thing have the same power? How much time?
What is your charger?
It's dead.
Are you using?
I don't know.
No?
Can somebody get it from my office? Like,
I have like, what model is this computer? Because I have a XPS 13. The cable for them.
Why is not everything USB-C?
What's USB-C?
Can you hold on for like 15 more minutes?
Maybe, what's the time right now?
I can't,
It's
what's your
11:42.
model? Where's
It's 217. It's 217. My desk is on the left and it should be in my backpack. Yeah.
This is a high complexity task.
We're gonna take these parts.
Yes, maybe I should
Okay.
quickly.
I don't think we're
Um,
gonna do this.
I guess the more interesting part we haven't been through. But also another thing I wanna notice is that we could show a similar separation between RP parallel and DP parallel. Again, instead of using k-fold for addition, we could just use a Doi-Joseph function or some function which achieves an exponential separation. And yeah,
It's even better than exponential separation, right? It's
Yeah.
unbounded separation.
yeah, yeah, sure.
They made that Deutsch Joseph unbounded separation. Constant versus.
Yeah, right, it is unbounded.
Can you explain again why RP parallel, how does RP parallel relate to R? Like,
So RP parallel is like the randomized query complexity when you allow like P parallelism. And when P is 1, you get R.
yes. So like, but here you're trying using that RP parallel is lower bounded by R divided by P.
Yes.
Okay.
Because you can simulate a P parallel Q query algorithm using PQ sequential queries.
So you lose a factor of 1/n².
Yeah.
there, but that's fine.
And so another thing I wanna just note is that we could lower bound the block sensitivity to be n squared, and so here we could say something about the block sensitivity of the cheat sheet function, which would be sort of non-trivial to think about because lower bounding is easy because you just need a bit string, and you wanna like you can evaluate like whatever block sensitivity you get, but when you're maximizing over all inputs, it could get really hard. So this could be like a new way.
Are you saying the block sensitivity must be at least, at most something, otherwise you run afoul of Stacy's result, basically?
Yes,
Yeah.
yes. So we can use that result, and this method of showing exponential quantum parallel advantage to upper bound block sensitivity. So this could be another way to upper bound. Where? There we go.
Something went wrong. Oh, no. Gary?
Oh, switched off.
What did your computer die?
Yeah. It was
Did you just not make it, or did something else go wrong?
The group is the host.
Okay.
That's a very bad one. Well, at least we got to the central result, so we know what we're on.
Well, I think the more interesting part is left to.
Bummer.
What's happening?
Could you join the Zoom?
I can see it here.
Join the Zoom.
Oh, that's, you have to join the Zoom again? Maybe you kicked yourself out of the Zoom?
Wow. Okay, so now the more dramatic question is that is this exponential speed up satisfying? Because what we are just doing is we have like a lot of parallelism, and then we took a super quadratic separation, and we had a lot of ports, and we just amplified that separation into an exponential separation in the parallel world. So is this even like it's quite interesting, but it's sort of not new in a sense. And so one could ask a question that is super quadratic speedup necessary to achieve exponential parallel speedup? And the answer is no. That we could come up with a function that has the same sequential query complexities, sequential R and Q query complexities, and it still achieves an exponential quantum advantage. So this is our main contribution. There exists a function whose randomized query complexity is polynomial in the domain. The quantum query complexity is pretty much the same as randomized. The randomized parallel query complexity is also polynomial, and the quantum query complexity is still 3. And I guess the main technical ingredient is this partial function, which basically has the same quantum and randomized query complexities, but it parallelizes perfectly quantumly, but it doesn't parallelize at all classically. And maybe I should describe the
Right, this is more fun.
yeah, I'm sorry for
No, it's okay.
so maybe I should describe some intuition about the construction. So how would we usually construct a function which is as hard for a parallel classical computer as it is for a sequential classical computer? So it is this question is very well studied. We could just have something like a pointer chasing function. So what we have is like k functions f1 through fk, and we take each fi that is hard to compute classically except f0 because we want to chase the pointers, but when you compute f sub I, you get a hint that you can use to compute f sub I plus 1 fast. So even if you have a lot of parallelism, your best bet would be just to walk through these functions, and the goal is to compute f sub k. So you have access to it, but you can try to compute it on its own, but it would be very hard. So your best bet, even if you have like sufficient parallelism, you just walk through those functions. But then the problem is that it would also be hard for a quantum parallel algorithm. So how do you resolve that? And I guess one idea is to just take all those f sub i's that exponentially separates quantum and classical. So then intuitively, for a classical algorithm, it's still hard, but a quantum algorithm has access to f sub k, and it could just solve it fast. It can just ignore f1, f0 through f sub k minus 1. But then it's also easy for Q, for a non-parallel algorithm, because it also has like you can solve f sub k fast, and a quantum non-parallel algorithm could just solve f sub k directly. what do you do with that? This is easy to resolve. Then you have your, you ask to compute a property that depends on all f sub i's instead of the last one. Maybe I should describe the formal construction. So we'll have like k many blocks, where each block comprises of little n minus 1 instances of Simon's problem, where little n is the size of the Simon's secret. If you recall Simon's function, you have like an n-bit, little n-bit secret, and the size of the input is capital N, which is 2 to the little n. And now what you do is, you, in each block, you have little n minus 1 secrets. So, if you find those secrets, you get some hint about the next block. And what would that hint be? So the concatenation of the first bits, this is the reason I chose little n minus 1 blocks. Because if you just take like 1 bit from each of the Simon's instances, let's say the first bit, that would form the last n minus 1 bits of all the Simon's instances in the next block.
But you're constructing it to do that.
Yeah, this
Using the
is
secrets that have this property.
Yeah,
Yeah, okay.
yeah. I'm also I'm describing it algorithmically, but it's a construction.
Sorry, I can move on. So you get n minus 1 bits by taking the first bit of each of n of the n minus
Right.
1 different bits, and then that gives you an n minus 1 bit string.
Right.
And that n minus 1 bit string is
Is going to be the secret of the next block of all the n minus 1 functions in the next block.
they all have the same secret
Right.
except for the
Oh,
Right,
yeah.
they are very correlated, but we do not care about that because little n will be smaller, will be too small for us. So
So it doesn't, it's not a problem that they're all correlated?
yeah, the instances in each block are very correlated, but we just need to show that computing one of them is hard.
I don't quite get what's the point of having many, like, because there's n, the secret is n bits, right? So there's only two, like, there's two secrets, just like every instance in the next block has one of two secrets.
Right.
So like,
But then it is hard to compute if you do not have the trapdoor. Once you get the trapdoor, those functions are very easy to compute. And that's what we're giving. We're giving a hint after resolving each block.
one instance in the next block, that would already give you the trapdoor for the rest.
No, each instance gives you 1 bit of the trapdoor.
No, but so you, in block J,
Right,
you get an n minus 1 bit string.
right,
And now you go to block J plus 1.
right.
If you just in block J plus 1 computed a single secret, that would also give you, you could also look at the last n minus 1 bits of that to get a trapdoor. Or am I-
No, the trapdoor is formed by looking at the first bits of each of the secrets in a block.
J.
In
And
block
what,
J.
but what it is, if I understand correctly.
Yes. Yes,
It is the secret.
Sure.
So if you learn any of the n secrets in the next block,
right,
you will also learn the trapdoor.
right. But then learning that is hard. Because you have
Yeah.
to solve a Simon's problem.
I guess I'm just like not seeing why you have these n different instances. It seems like if you, once you solve one of them, you've now
Right.
got a trapdoor for the rest.
I guess the reason we did it this way, I'm sure there would be other ways to do what we're trying to do. But the reason was, because we don't want the correlations to go too far. So we just want, like if we solve like a few, some Simon's problem in one block, we just want that to be correlated with the next block only.
Yeah, I was just, because when you say Simon's problem, do you mean like you find the n bit shift?
Right,
So the output of the problem itself is already n bits.
right.
So it's like n squared, little n squared bits you get. You're not using the decision problem version.
Right.
Okay.
Yeah, you get n square bits, but
It'll be a bunch of repeated.
Yeah. Yeah.
The same two n bit strings.
Yeah, but basically it has n bits of interval.
Leave it, I just don't. Try to follow that, okay, that's fine.
So why is it even useful to sort of like feed trapdoor information into the next level? Because a quantum algorithm can compute those Simon problems anyway without trapdoor information.
Yeah, that's right. But we also want a classical computer to be able to walk through these
I
Simons
want it
functions.
also to be easy for the randomized algorithm.
You do? Don't you want to use parts for doing this?
You want the randomized.
Yeah, you-
complexity the same without parallel.
Oh.
So you also want to help, so this is done to help the randomized algorithm.
I see, okay.
A quantum algorithm could walk through
Yeah.
this or could
Yeah,
just
yeah.
independently solve all of them
Mm.
in any order it likes.
And now the global one.
And
Sorry, what's J?
Huh?
What's J? Or J in the second?
J is just an index denoting instances in the ith block. So if I say fi comma j, I'm saying it's the jth instance in the ith block.
I think if you go to the second bullet, then the second line, like if you go from the top line fi1 to fin minus one, and the second one, I would expect the second line of f's. I
Oh,
would expect the last one also to be.
it should be n minus one.
Yeah, that's okay.
Oh, it should be n minus
I
one.
thought some extra thing, whatever. Yeah, I would also expect.
Yeah, thanks. Another thing too. Yeah, so also the first n minus one bits you get for free, because because you want to help the classical computer. Yeah, and so the output is the global properties, like the parity of the first bits of all these k times n minus one instances. And yeah, so this is like a picture. So you have like the trapdoors, and the trapdoors are being like fed to each of the next blocks. And this is like the picture of a block where you compute each function, but all of them have like the same trapdoor in one block, and you get these n minus one bits, the first bits, and then you get the trapdoor for the next block. And maybe we could just think a little bit about what the bounds would be. So a classical algorithm could just walk through the blocks. So it has to solve like k. So given a trapdoor, it only requires 2 queries to solve a Simon's problem, right? Because you know the n minus one bits, and you can just choose. You can, yeah, it's easy to make only 2 queries and solve it. So, so classical algorithm would just need to do this k times n minus little n minus one, but little n minus one is logarithmic in k, so the query complexity is k for classical algorithm. For a quantum algorithm, we define a global property, and we could reduce just so that we could reduce parity to our function, and so we get a lower bound of k. So the classical and quantum query complexities are the same. A QP parallel algorithm will just simply solve all the Simon's instances in parallel, because those instances like could be solved in parallel, and also the Simon's function itself could be parallelized. So it could be parallelized, it could be fully parallelized. Right.
Because this sort of ignores the trapdoor information that you get from the previous.
Right. Which is fine for but now the hard part is to show that a classical algorithm has to make certain number of queries. I'm sure this bound is not tight, but we just have to show that even when p is like some polynomial, I would like to choose it to be n to the 1/4 for reasons you can see. So even if p is some polynomial, your query complexity is still a polynomial. And this is the hard part, so we don't talk about that. You give it as an exercise. I have a slide though on this, but I could skip it.
No, please.
Okay. So yeah, so the point is that there will be very strong correlations, and how do you ignore those? And so what we do is like, we describe a game, and then at each round, like the algorithm makes some queries, and then we answer those queries, and we also give them more information. And it makes it easy for the algorithm, but it also makes our life easy, and it's easier to show that it's hard. And yeah, this is like the very broad, very big picture idea. And we use Yaw's lemma, and we come up with a certain distribution, and we show that that distribution is hard for any algorithm. And so we just need to show deterministic lower bound. Yeah, and now I could describe f total from f partial. F total was the function which achieves an exponential quantum parallel advantage, even though the advantage is, even though the sequential advantage, there's no sequential advantage. So this is not, this is just like using some standard properties. So we know that there exists a function which has a quadratic separation between quantum query complexity and certificate complexity, which was constructed in this cheat sheet paper. They call it PKK, which is like a composition of block K-sum with K-sum. We don't want to know what that is. For us, it's a black box. We call it H. We just know that it has some properties, that its certificate complexity is small, but its quantum query complexity is huge. And we let F total to be just the cheat sheet version of the composition of F partial with this function. And again, we'll have like similar upper bounds. So maybe we can talk a little bit about the bounds of F total. So a randomized algorithm only needs to make kn square queries. Is it already lunchtime? Just give me 3 minutes.
Yeah, sure.
Um,
I mean, I'm making decisions for everyone. Go, finish it.
Yeah, so this upper bound just follows from algorithms for H and partial. Nothing too complicated. And the quantum lower bound follows by a composition theorem, and we know tight lower bounds for H and F partial. The parallel quantum algorithm would just do something similar that I described for the regular cheat sheet version. And the classical algorithm, the classical parallel algorithm, we need to show that it's hard, and that is hard to show that it's hard. And so again, we'll basically skip it. I think I have a slide though, but
You skip it, you mean you leave it as a conjecture, you mean you don't discuss it here? You just keep this period.
I mean, it's somewhere, but as in like I'm not going to describe it.
Okay. There's a proof, he just doesn't want to talk about it.
Yeah, so basically if you choose k to be n to the 1/4 and p to be n squared times n to the 1/4, you get all the desired properties. And one question you might ask is, what is the separation relative to the domain size? And I think it was like 1/49 or something, but we don't really care about that for now. Yeah, and I could just describe some intuition on why this is hard. So recall that in the regular cheat sheet parallel lower bound, we use the randomized lower bound to show a lower bound on RB parallel. But here we can't do that because we want to use the bottleneck that we have for the F partial function. And so what we could do is like we basically adapt arguments from this cheat sheet paper to show a tight composition theorem for randomized parallel query complexity with the inner function being this weird function h. And we also show that even for a parallel classical algorithm, the cheat sheet cannot help you as long as C is large enough. And this might be independently interesting. And here we are. So we leave some question. Basically, everything is open in this field because I guess nobody like really studied it. Excuse me. After that. Nobody studied after that. So the one question is like this question we never really cared about is what is the largest separation between QP parallel and RP parallel, and also QP parallel and DP parallel and RP parallel and DP parallel. We know it's exponential and unbounded, but we don't know what the tag bounds are. This is my favorite open question. It is to say that if I allow a classical algorithm, because classical algorithms suck. So if I allow classical algorithms some polynomial parallelism, some polynomially more parallelism than I allow a quantum algorithm, can we show that then a classical algorithm could simulate a quantum algorithm, which is polynomial overhead?
This is false for P with one, right? Or you're talking only about total functions. You're talking only of total functions here?
Yeah.
Okay.
Yeah. Oh, yeah, I should mention. Yeah, sorry. Yeah. So for dual functions, can we show something like that? That if we allow polynomial overhead and the parallelism can, yeah. So this is my favorite question. And again, some people would argue that our construction is not natural. I don't totally agree with them. But that's a question for them.
What's a natural function?
Maybe, I don't know. I'm not saying our constructions are unnatural. So yeah, is there a natural function that could achieve such an exponential speedup? And that's about it. Thank you.